All right, guys, so today we're going to be looking at the Momentum in Sports worksheet together. All right, now in class we started talking about momentum and impulse and conservation momentum, and so what I'd like to do is just make sure that you're comfortable with these different ideas. I know that sometimes they can be a little bit challenging, especially when we mix them with things like Newton's laws and other ideas, velocity, these other things that we've been talking about all year. And so one of the things that you'll notice in this worksheet is that we do go back and forth between those different ideas. The hope is that in the long run, this will be helpful to you. If you decide to go on with physics in your future, that you will be able to deal with physics in the sense that, you know, real life doesn't say, hey, this is momentum, can you use momentum? No, real life doesn't do that. Neither will an assessment, right? An assessment isn't going to say, this is a momentum question, use momentum, use this equation. You have to be able to read the question and make decisions based off of that. And so this worksheet will go back and forth between a variety of different things in the hope that we can kind of talk about how to use that. Okay? So let's go straight into it. We've got momentum in sports. Our first sport here is pool billiards. In a game of pool, a player strikes the cue ball, which is 0.17 kilograms. That's 170 grams. So that it travels with a speed of 2.7 meters per second. How much momentum does the cue ball have after being hit? So this question is just straight up, find the momentum, right? And we know that we can find the momentum, P equals mv. That's in your formula packet, that's on your data sheet. So we put in the mass, which is 0.170, 170 grams, 0.170 kilograms, and we multiply by the velocity of 2.7 meters per second. When we put those numbers in, it should just be 0.17 times 2.7, and I get 0.459. And so I get that my momentum is 0.459 kilogram meters per second. And that's the first question. It's just straight up calculate momentum, all right? Let's move on to the second question. So in the second question, it says, a short time later, the cue ball strikes the two ball. That's what we're seeing in the image here. The white ball, the cue ball, is hitting the two ball there, which also has the same mass, which was initially at rest. After the collision, the cue ball travels with a speed of 0.4 meters per second in the same direction as before. That's important, in the same direction. Assuming that the ball strikes straight on, complete the table for momentum below and calculate the speed of the two ball after the collision. Remember that momentum is conserved in a collision, so the total momentum before should be equal to the total momentum after the collision. Use V for the final velocity of the two ball. All right, so I'm going to go ahead. Let's scroll up a little bit here. Okay, we are going to need this 0.459. 0.459, remember, was the momentum of the cue ball. So I've already solved for that. So this one is 0.459 is the momentum before the collision, before the interaction. Okay, momentum, remember, is P equals mv. So the two ball, remember it said that the two ball was at rest, right? Strikes the two ball, which was initially at rest. And so if its velocity is 0, then mass times 0 will give us 0 momentum. So the total momentum of the two ball is 0. And so before the collision, we already know we can add these two together, and we get a total momentum of 0.459. We just add the two momentums together, and that is the total momentum of my system, the two balls, right? Now, we're going to look at after the collision. So after the collision, what do we have? Well, again, I'm going to use mv for momentum. So the mass of the cue ball, the white ball, is still 0.170. And I'm going to multiply that by its velocity. Now, up in the question, it says, after the collision, the cue ball travels with a speed of 0.4 meters per second. So we're going to put the 0.4 there, and that will allow us to calculate the momentum of the cue ball after the collision. So 0.4 times 0.17 gives us 0.068. 0.068. And then for the two ball, the two ball, and recognize it does say, I'm going to remind you, it does say that the 0.4 is in the same direction. That's why I put positive 0.4 here. My initial velocity was positive. My final velocity is in the same direction, so also positive. That'll become important in later questions. Okay, the two ball, it says we don't know, but that's what we're looking for, right? It asks us to use V for the final velocity of the two ball. So the two ball also has a mass of 0.17, but then its velocity is this unknown V. So to get the final momentum after, I'm going to add these two numbers together. So I've got the 0.068, and I'm going to add the 0.17 V. So this is already a little bit different from the one that we did in class. In class, these two things stuck together, they had the same speed, and I could add them together as like terms. In this one, the top number, the 0.068, doesn't have a V on it, so I can't combine it with that one. So I'm just going to write this. Don't freak out. It's okay. It's fine because I still only have one variable. It doesn't matter that I don't know what V is. It doesn't matter that I can't combine those, because what I'm going to do now is the same thing as before. I'm going to say that I know that before the collision, the momentum has to be equal to the momentum after the collision. Therefore, I'm going to go 0.459 is equal to 0.068 plus 0.17 V. Just like that. And now it's an equation that I can solve. This is just a math question. So I'm going to get rid of the thing that's being added first. So I'm going to subtract the 0.068 from both sides, 0.068. And so this one, that's going to go away. I'll be left with 0.17 V. And then on this side, I'm going to have that, and then the 0.459, and I'm going to get 0.391. So 0.391 equals 0.17 V. Now I'm going to divide both sides by the 0.17, divide this side by 0.17, divide that side by 1.7, and I end up getting 2.3 meters per second equals V. All right. Now, hopefully, our answer is reasonable. Remember, in the beginning, we had the cue ball with a certain amount of momentum. It had its mass, and it's had its velocity going in that positive direction, right? When the cue ball hits the two ball, it's going to transfer some of its momentum to the two ball. The two ball is going to gain momentum. It's going to gain speed, and the cue ball is going to lose momentum. It's going to lose speed, and that's exactly what we see. We see that it loses a certain amount of momentum. Therefore, the two ball has to gain that amount of momentum. All right? And that's what we see happening here. So we do have our answer of 2.3 meters per second. All right? Now, in part C, it's going to ask us to calculate the impulse on the two ball, the impulse of the two ball. What's the change in momentum of the two ball? Well, we can do that now, right? Because we know that it started with 0 momentum. And now it has 0.17 V, but V is 2.3. And so I can now find the final momentum. So I'm going to go 0.17 times the velocity, which is 2.3, and I get 0.391. So therefore, ball 2 started with 0 momentum and it ended with 0.391. So remember that. I'm actually going to leave this up on the screen as I scroll up so that we can now do question letter C there. Right? And I'll erase this in just a minute, but for letter C, we need the impulse of the two ball. So the impulse of the two ball, remember there's two different ways that we can calculate impulse. One of those is by finding the change in momentum, doing the final momentum minus the initial momentum. The other way that we can calculate impulse is using the force, I want to do change in momentum, impulse equals the force times the time. Now, I don't have either of these at this point, but I do know this. That's what I was just talking about, right? The final momentum is 0.391. And so I'll put that in here, 0.391 for the final momentum, and then minus the initial momentum, and the initial momentum was 0 from my table. You can see the table on your page. Unfortunately, I've had to scroll it up, but 0. So I do that, and my final answer is 0.391 kilogram meters per second. Please do remember to include your units. All right, so there we go. The impulse of the 2-ball is 0.391. Okay, so now I'm going to erase what we have here. If we have to come back to it, then we will. All right. Okay, now we want to do letter D. If we assume that the time of contact of the 2 balls is 0.001 seconds, what force was exerted on the 2-ball? All right, we can do this now, right? Because we now have the time and we have the impulse, the change in momentum. That's what we found in this step right here. So now we get to use that other equation. So we get to go delta P equals force times delta T. We put in the change of momentum, which is 0.391. We don't know the force. That's what we're trying to solve for. And then the time is what it gives us here, 0.001. All right, so we're going to take this and divide by 0.001, and we get the force. And hopefully when we calculate that, we get 391 newtons, which is the force. All right? So not too bad, right? It's just a little bit at a time. Hopefully you're getting a little bit more comfortable with this as we go. The next question is, using Newton's laws, specifically the second and third laws, describe why the cue ball slows down and the 2-ball speeds up. All right, so let's talk about it. We've got the cue ball. The cue ball is coming, and it's going to hit the 2-ball. Now, when the cue ball hits the 2-ball, it's going to exert a force on the 2-ball. So that's the force of the cue ball that's going to push that to the right. Therefore, the 2-ball should speed up, right? It was at rest. It should gain some speed, right? Pretty straightforward. Now, why does the cue ball slow down? Well, if we're talking about Newton's laws, the reason why it slows down is because if the cue ball exerts a force on the 2-ball, then the 2-ball exerts a force back on the cue ball. That's Newton's third law, right? Whatever force it exerts on the 2 exerts back in the opposite direction. The same force, same magnitude, same type of force, just in the opposite direction. So we exert a force in the backwards direction. Therefore, if it's moving to the right and the force and acceleration are to the left, it is going to slow down. All right? And that's all we need to do for E. That answers the question. Okay? Let's scroll forward. And that's it with the pool balls. All right. Let's move on to a different sport. This is one that you may or may not be familiar with. This is a sport called curling. All right? And you may have seen this in the Winter Olympics. Okay? But in curling, the person they're on ice, so basically no friction, frictionless as much as possible. They hold a stone, this is called the stone, and they hold it, and they go and they walk or run forward, and then they slide, and while they're sliding, they give the stone a little push, right? And then the stone goes down the ice, and there is a little bit of friction, and so as the stone goes down, it slows down, and they're trying to get the stone to stop in a specific area. And whoever gets their stone closest to the center area ends up winning that round, right? And so you slide, and at some point you push the stone forward. That's the interaction we're going to look at right there, is what happens if her and the stone are sliding together and then she pushes on the stone. All right? That's what we're looking at here. So we've got her, she's about 50 kilograms. She's moving to the left. Left is negative, okay, with the speed of 1 meter per second while holding an 18 kilogram curling stone. She pushes the stone so that it's now going a little faster. The stone is now going 2 meters per second to the left. Though this isn't a collision exactly, it is an interaction between the two. She exerts a force on it exerts a force on her. Therefore, momentum should be conserved. The momentum before she pushes the stone should be the same as the momentum after she's released it, assuming negligible friction for that moment. And it is on ice. There is very, very little friction. So the first thing it wants us to do, calculate the initial momentum of the curler as well as the initial momentum of the stone. All right? So momentum, we know, is mass times velocity. Okay, I'm actually going to do it over here because I'm going to need this information in just a minute. You can do it right here, but I'm going to do it up over on the right. So first, I'm going to do the curler. Okay, so that's the lady. The lady's the curler. So her momentum, the momentum of the curler, this is the initial. So momentum of the curler initial at the beginning is equal to her mass times her velocity. Now her mass in the question, it says that her mass is 50 and her velocity is 1 meter per second, which means her momentum is 50 kilogram meters per second. Right? Okay, fair enough. The second thing it wants us to find in part A is the momentum of the stone. Okay, the stone is the rock that she's holding and that she releases that slides along the ice. So the momentum of the stone initially is equal to its mass times its initial velocity, right? Remember, she did it to the left. So this velocity, I apologize, that velocity should be negative. If that's negative, then the momentum is also negative because it is going to the left. All right? Now, she pushes the stone. The stone, this is before the push though. This is before the push. Before the push, the stone has a mass of 18 and it has a velocity of -1. Right? Because her and the stone are sliding along together at the same velocity right before she pushes it. Okay? So, mass velocity, and I get my momentum of -18 kilogram meters per second. All right? So that's part A. Not too bad. Okay? It's just asking me to find that momentum. Okay? So now let's look at part B. Part B asks us to fill in the table. Okay? You don't have to use a table, right? Very often in your formula packet in the data booklet, it just says this. It says M1 V1 plus M2 V2 equals M1 V1 plus M2 V2, right? This is just the momentum of the first object before, the momentum of the second object before. That, when you add those together, that needs to be equal to the momentum of the first object after the collision or interaction plus the momentum of the second object after the collision. If you have a more analytical mind and this makes more sense to you, you can use that. But if it's helpful to you to use the chart, the graph, then you may do so. Not the graph, sorry, the chart, the table. All right? So we already know that the curler had a momentum of -50 kilogram meters per second. That was what we found before. The stone was -18 kilogram meters per second. Now when I add those together, I have the total momentum before she pushes the stone, and that total momentum will be negative 68 kilogram meters per second. All right? Now, the question is, what is her velocity going to be after she pushes the stone? So her velocity, the V for the velocity of the curler after, that's going to be V. Okay, so after, she still has a mass. Remember, momentum is still mv. So her mass is still 50. But that's going to be multiplied by her final velocity, whatever her speed is after she pushes the stone. She still slides along until eventually she stops, but she does keep sliding after she pushes the stone. Okay? The stone is going to be 18 kilograms times its velocity. Now, if you remember back up in the problem, if you don't remember, you can go slide back up and look at the top of the page. But it says that the stone, when she pushes it, now travels at 2 meters per second. And it does say that it's still to the left. Obviously, that makes sense. She's sliding to the left, the stone's sliding to the left. She pushes it towards the left so that it is going down to the end of the pitch, or I have no idea what they call it. Okay, so this one would be negative 36. All right, so when we get the final momentum, we're just going to add those two together. So it's 50V minus 36. That's the total momentum after. Again, don't freak out that you don't know it. Don't freak out that you can't add those together. It's fine. Just write it down. That is the final momentum. We don't know what it is yet, but that's it. All right? Now, we can set those two things equal to each other. Right? The beginning momentum must be equal to the ending momentum, assuming that there's no forces, external forces that are unbalanced. In this case, we're ignoring friction. We're saying friction is negligible. Okay, so now that I've done this, okay, I'm going to go ahead and get rid of this. We're going to set those two things equal. Negative 68 equals 50V minus 36. So we're going to add 36 to both sides. That's going to leave me with negative 32 is equal to 50V. We're going to divide both sides by 50. And negative 32 divided by 50 is going to give me that V is equal to negative 0.64 meters per second. There we go. All right, so we've been able to do that. We put the information in the table. This is M1V1, M2V2. That's the total. M1V1 after the collision, M1V2 after the interaction, and then this is the total. Set those two equal, and we're able to solve for V. So we filled out the table, and we calculated the speed. Okay, the speed is 0.64. The velocity is negative because it's still to the left, right? Okay, let's scroll up just a little bit and see what else we got. Okay, I don't think I need these anymore. I'm going to go ahead and remind myself that the curler initially was 1 meter per second, and now negative 1 meter per second, and now it's negative 0.64 meters per second. The stone was negative 1 meter per second, and now it's negative 2 meters per second, because I think that that might be helpful as I go into answering the last couple of questions. Okay? So the next two questions are asking us to talk about it, to write about it, right? So in this one it says, using the principles of Newton's laws, explain why it makes sense that she, the curler, should slow down. Okay? So as she slides along, she's moving in this direction to the left. When she pushes on the curler, Newton's third law says she pushes on the stone. If she pushes on the stone pushes back on her. So if there is a force back on her, then there's a force opposite her motion. She's already moving in that direction, but if there's a force opposite that motion, then what that would mean is that she will slow down. The acceleration will also be in the opposite direction. She will slow down. And that should make sense. As long as that force is there, she should slow down. All right? That explains why the stone goes forward as well, because she exerts a force on it in that direction. It's moving that way. Her force on it is in that way. The acceleration is that way. When the acceleration and the velocity are in the same direction, it speeds up. Therefore, it speeds up. To the left. To the left. Next, using the principle of conservation of momentum for the curler stone system, explain why it makes sense that she should slow down. Okay, well, that's what we just looked at with the conservation of momentum. We just calculated that, right? What we saw was initially they had some momentum in this direction. So in the end, the total momentum still needs to be in that direction. But if she gives the stone more momentum in that direction, in order for momentum to be conserved, if it gains momentum in that direction, she has to lose momentum in that direction, or at least gain it in the opposite direction. And so that's what happens. The stone is smaller, so it gains some significant speed in that direction. It gains momentum. She is going to lose some of her momentum, but her velocity isn't going to change quite as much because she has more mass. All right? Hopefully that makes sense. That's using conservation momentum. And we're back. All right, so one more question. This is going to be our last one on this assignment. I know you're so sad. Things are almost over, but we're almost there. Okay, so this one again is back to American football, rugby. You can think of it however you want. We got one guy that's going to be running one way. The other guy is going to be running the other way, and we want to talk about what happens to that situation. All right, you can read the question. You've got it in your homework. We did a question similar to this before, but we'll now apply it to some real players. Jonathan Taylor has a mass of 102 kilograms. He's a running back for the Colts. He receives a handoff and sprints through the offensive line with a speed of 1.9 meters per second. He is met by Bobby Wagner, who is 110 kilograms. He's a linebacker for the Seahawks, so he is going to come up to him. He's going to try to tackle him. Okay, notice that again, he wraps up completely just like a good football or rugby player would, so the two players stick together after the collision. All right, so the first thing is it wants us to determine Jonathan Taylor's momentum before the collision. All right, so that's what we'll do first. Straight up, momentum equals mass times velocity. We know Jonathan Taylor's mass. His mass is 102. His velocity was 1.9. And so we're going to do the 1.2 times the 102 times 1.9. And I get 193.8 kilogram meters per second. Please do remember your units. Always write. The more often that you write the units, the more likely it is that you will remember the correct units when the time comes, and you won't have to worry about it. You're just used to momentum is kilogram meters per second. Okay, so we got the momentum for Jonathan Taylor before the collision. All right, now we'll go ahead and scroll up. The next question is determine Bobby Wagner's momentum before the collision. And obviously the direction matters. Okay, so from the question, we knew that Bobby Wagner had a mass of 110, and he's going the opposite direction at 1.6. Okay, so we'll go ahead and go here. So that was Jonathan Taylor was 193.8. Bobby Wagner was 110. And he's traveling at negative 1.6 because he's going the opposite direction. And if I multiply 110 times that negative 1.6, I get negative 176 kilogram meters per second. Okay, so that would be the answer to B, is negative 176 kilogram meters per second. Now we're going to complete the chart. We're going to answer the final question. Okay, we can add those two together to get the total momentum before. All right, so we've got the negative 176 and then the 193.8, which will give us 17.8. Okay, and you may look at that and be like, well, that's not very much momentum. There's a lot of mass and a lot of velocity moving. Well, yeah, that's true, but do remember that they're moving in opposite directions. The positive momentum and the negative momentum are going to cancel out. Remember when we talked about the gun in class, the bullet went one way, the gun went the other. They were both moving quite fast, but because one was positive, the other was negative, it was possible that the total momentum added up to 0, which is what the momentum was before. So same thing here, is that they're moving in opposite directions. Therefore, the total momentum at this point is only 17.8. All right? Now, after the collision, now remember they wrap up, they connect, they're going to go the same speed. So we're going to have Taylor, which is going to be 102 times the final velocity, whatever that is. And then we're going to have Wagner, which would be 110 times his final velocity, whatever that is. Those two V's will be the same because they're connected together, they're moving together. And so my final momentum will be 102 plus 110. This time I can put them together because they're like terms, they both got V. So this is going to be 2, 1, 2, V. These two must be equal. The momentum before and the momentum after will be equal from the collision. And so I'm going to take that 17.8 and I'm going to divide it by 212. And I'm going to get 0.084. All right? That doesn't seem like a lot, right? But you've seen this. If you watch enough football or you watch enough rugby, you have seen this. You've seen two guys going straight at each other and they hit and they basically stop where they're at. It should make sense, right? Yes, Taylor is moving faster, but he has a smaller mass, right? Wagner has a bigger mass, but a smaller speed. His momentum was a little bit less, which means that the final motion should be in the direction of Jonathan Taylor. He was moving to the right. We notice that our final velocity is to the right, but it is very small now that they've collided and they've opposed those two momentums and combined those two so that we don't have a lot of momentum for the amount of mass we have, which means they can't be moving very fast. Right? At first, it seems a little weird, but once you think about it, you've seen it. You've seen it before. Two guys go head on, and when they hit, they lose all of that speed. The momentum is still conserved because of that positive and negative. But we end up getting velocity of 0.84 meters per second. All right? Now, obviously, in real life, they're pushing off the ground. There's a lot of other things going on there. But when we get it down to the basics, the simplest situation, if we were to ignore all the other forces, this is what it would end up as. All right? Okay. And that, my friends, is almost the end. This is the last question right here. Conceptually discuss conservation of momentum and why the velocity in part C makes sense. Oh, snap. I just did that. So if you weren't looking at that part, just rewind the video. You can go watch it again. We're talking about both magnitude and the direction, right? We talked about how big the velocities were. We talked about the mass. We talked about the velocity. We talked about the momentum. We talked about the conservation of momentum, how the total momentum was small. So once they stick together, you don't have a lot of momentum, but you got a lot of mass there, which means that the velocity is going to have to be small. We talked about why it made sense that it was positive, right? We talked about why they almost balance out, even though one's faster, one's bigger, right? So hopefully that made sense in answering this final question on the worksheet. All right? So that's it for today. I hope that was helpful to you in trying to understand a little bit better this idea of conservation of momentum. I hope that was helpful in using the idea of conservation of momentum to talk about things and also connecting it to the forces and Newton's laws, which we've done before. All right, so that's it for today, and I wish you luck, and I'll see you next time.